Hi all, this is Abhishek. I work as a technical architect with a leading organization. I'm an expert in Microsoft .NET, Azure Platform as a Service Cloud, artificial intelligence, intelligent automation, and machine learning. And today we will see the next in the series for machine learning concepts for dummies, where we will see a new concept called as gradient descent in the context of linear regression. Okay. So before we get into this, I would strongly recommend you to go back and have a look at the previous 8 videos for this series to make more out of this video. And gradient descent is a very important concept when we are dealing with machine learning models. Okay, so let's get started. So, what a gradient descent is? Gradient descent is a optimization algorithm. What I mean by that is, by applying gradient descent, we can have the best optimal algorithm or the best fitting algorithm for a linear regression problem. So this is helpful in getting a optimized algorithm for a linear regression problem. So how we get the optimization? By deducing the local minimum of a cost function or of a function by adjusting its parameters iteratively. In my previous video, we saw a cost function and we saw that as the value of the parameters increases, the cost function value decreases to a local minimum and then it starts increasing again. So by using gradient descent, we can deduce or reach the minimum of that, and we can deduce the best fitting parameters, and hence we can optimize the algorithm. We will see that quickly. Okay. So what it does, it helps to find the values of parameters or coefficients of a function at its local minimum. Okay. Let me try to explain you these 2 points. They are very important. So here I have a cost function plotted for the b values. B values are in the x-axis, which are increasing, and we have in the y-axis the cost function. And we see as the b value increases, the cost function value decreases and it touches the local minimum and then it starts increasing. So our job is to find this value or reach out here. Let me give a quick generic example of gradient descent. For example, you are at the top of a mountain or a cliff and you want to come to the bottom. So how will you go? So there will be several possible ways to descend down to the bottom, but you need to take the quickest and the accurate path where you will reach exactly to the bottom. In the same way, our algorithm can be anywhere in this point. Maybe like for example, let's take this point and we start our descent from here. So our steps should be accurate enough to reach to this local minimum, and we should also reach quickly. Our steps should not be something like it should miss this point. Like for example, we are descending from here, we are taking some longer steps and we tend to miss this point, and from we reach here and we tend to skip this, and then again we start moving upwards. So in this case, like we are missing the local minimum and we have a different local minimum, that is this point. So we should not be doing this, hence our things should be quite accurate. Okay, so in case of gradient descent, let's take at this point, like say like b of I is computed iteratively as b of I equals b of I minus alpha into the slope or delta by delta b of cost function, that is the differential of the cost function. Okay, that is nothing but the slope. So let us consider this point. Suppose we are at this point here and we need to descend down. So what we will do first is we'll find the slope, that is delta by delta b of cost function. So once you have found the slope, then we need to find the learning rate, that is the step we are taking towards the x-axis. So this is the learning rate. from here to here. So this value is the learning rate, and this is the step we are taking to descend down the algorithm, or rather descend down this curve. So once we have found this learning rate, again we come like maybe like we reach this the point out here. At this point of value, again we compute the cost function, the entire cost function, and then we again find a slope, and again we compute the learning rate, and then we move one more step, or like one more that is equivalent to the learning rate towards the x-axis. In this way we descend to the minimum. We should be very careful that the learning rate or the steps are not too big. If it would be too big, we'll miss the local minimum, and it should also not be at the same time too small, else it would take a long time to reach the local minimum. Okay, so what we saw previously was a batch gradient descent. In case of batch gradient descent, we are at each of the point we are taking a summation of the difference between y actual and y predicted square divided by 2n. So for we are considering all the values of y for a particular b value at a particular point in the graph. For example, at this point, whatever would be the all the y values we are considering. So what happens here is it affects the computational efficiency because we are looping through and considering all the data points and we are summing it. But we have another kind of gradient descent, that is stochastic gradient descent. In case of stochastic gradient descent, the data set is shuffled randomly. Cost is determined for each of the data point and not for all the data point. That means the summation is ignored. For each of the data point, the cost is determined and the gradient is determined. So we don't have any summation here. So what it means here is the stochastic gradient descent helps in quicker descent due to increase in computational efficiency, and the result is accurate. Okay, so through stochastic gradient descent, we are considering each of the data point and we are finding the cost for each of the data point instead of all the data points. So this summation is ignored. So this has to be noted. Okay, so this is what I had planned for the gradient descent, and I hope you like this. So thanks a lot for being patient. Lot of new videos for this series are in the way, and hope you like this as well as the entire series. Thank you.